The purpose of this presentation is to show how the blending value of ethanol is significantly higher than some may recognize. The data used for this video presentation comes from two recent Society of Automotive Engineering or SAE papers and a refinery blending guide published in 1989 by HPI Consultants. We will specifically be comparing ethanol and toluene, which is one of the highest octane petroleum-based aromatic components of gasoline used by the oil industry today. Toluene, technically called methylbenzene, has been identified in various studies as a toxin. The EPA's 2007 Mobile Source Air Toxic ruling assumes that it takes twice as much ethanol as aromatics to achieve the same octane value, but you will see they have it backwards. Ethanol isn't new to the automobile industry. Henry Ford was the first to use and promote the value of ethanol as a clean-burning, high-octane fuel back in the 1920s. Even back then, Big Oil was able to control the market by pushing lead into the marketplace, which also created a significant health issue. How ironic that nearly 100 years later, the debate is still going on over the issues of octane. It is interesting that when you research octane on the internet, the octane values of ethanol varies. For mid-level ethanol blends such as E30, the blending value is uniquely different. When you look at any fuel pump in the United States, the pump label gives an octane rating, also referred to as the anti-knock index, or AKI. To calculate the octane or anti-knock index numbers, which are posted and required on every pump, the following equation is used. Research octane number, or RON, plus motor octane number, or MON, divided by 2. All the following charts will use the same parameters, with the horizontal axis being simply adding ethanol or toluene until the sample is 100% ethanol or 100% toluene. The starting point is a consumer fuel being 0% ethanol but meeting 87 octane. Gasoline today can be a mixture of hundreds of different components. The impact of the shaded area is most important, as no single component can make up over 20% of a gallon of gasoline. Other than ethanol, we will focus on the first 30% of blending. Most engineering studies will put ethanol at 100 octane or anti-knock index, but many references list 110 to 115 octane for ethanol, though never specifying anti-knock index or research octane number value. This is confusing to most people, so this presentation will use octane or anti-knock index, just as if it were labeled by any US fuel pump in any EPA model, or even as found in the Oil Refinery Handbook. Toluene is one of the most common sources for increasing the octane of petroleum-based gasoline at oil refineries today. This is supported by several very large market fuel studies, such as those performed every other year by the state of Texas and annually by the US Auto Alliance. Pure toluene is listed with 112 octane or anti-knock index. Note here that toluene appears to have much higher rating than ethanol. The octane blending value shown here was taken directly from the Refinery Handbook and confirmed in supporting SAE papers. Since gasoline typically averages 25 to 30% aromatics, the important evaluation for toluene's octane should be below 30%. When an additional 30% toluene is added to increase the octane of consumer fuels, the value of toluene is actually 104 octane or anti-knock index. When evaluating where to get the maximum octane value out of ethanol, the first 30% contains the most benefit. These octane increases are referenced in various Society of Automotive Engineers or SAE papers. The HPI Consultants Refinery Fuel Blending Handbook shows 120 octane or anti-knock index as the blending value for ethanol. This is also before much of the cooling effect is considered, which also enhances the octane performance. While octane measurement standards will not change anytime soon, this blending value has only recently been fully tested by the automotive industry. The EPA has stated that it would take twice as much ethanol as aromatics to achieve the same octane value. This is not correct when using real-world blending practices. For reasons such as toxic emissions, vehicle performance, and cost, you would not want to see aromatics blended into the consumer fuel supply over 30%. So why would you only model ethanol at 100% of pure ethanol? There is nothing in the gasoline pool that can economically compete with ethanol. It is interesting to note When you look at a 20% ethanol blend, it is higher in octane than that of premium consumer fuel blends of today and would sell at a lower cost than an 87 octane blend with no ethanol. And when you add the emissions reduction, why is ethanol being overlooked? Besides protecting market share, could the biggest obstacles to the higher blends of ethanol be that oil companies don't like the thought of octane competition? It's time to get the facts straight on ethanol's value for both emissions and for the consumer's wallet.